All right, so good afternoon to everybody who's hunkered down and sheltering in place wherever you may happen to be. We have a great friend of the community who's going to give us a quick little talk today on some of the work that he's been working on since he left PSC a couple of years ago and went off to Google. Mathis, who many of you probably know pretty well, is going to be talking a little bit about BBR and probably giving us a little bit of a history of TCP as well. We've been having a couple of technical glitches as we've been going through this, but hopefully that won't stop us from hearing what Matt has to say. So Matt, I will turn it over to you.
Yes, thank you. It's actually good to be talking to this community again. I think I'm going to try and doing that a little bit more often. Let me say a few things. Well, I tested these slides. I tested Zoom last night. I don't normally use Zoom. I use the Google products, and it's interesting. It looks like the underlying infrastructure is all the same, and so a lot of the stuff works the same way. But we're having a little bit of problem here with the compatibility and present mode. Yes, I'm going to talk about sort of a brief history of TCP and how some of the big things came to be, and then why BBR is such a radical departure from the past and why it makes sense now, and what's sort of driving the evolution and introduction of BBR. I'm sure this is history for most of you, but the base specification for TCP is almost 40 years old. 7 years later, Van Jacobson's landmark paper defined the framework for essentially all of the congestion work that's been done since that time. An important thing to think about here is that the base specification gives a sort of a narrow definition of correct operation, and Van's 88 algorithms give a stronger definition of efficient operation, efficient use of resources, not being wasteful, and being fairly quick. The key, there are several algorithms about things like RTO and stuff like that. I'm sure many of you who have seen the paper, but the concepts of packet conservation and self-clock are really core to the ideas in that paper. And a lot of the stuff is derived from those core principles. Another thing that the paper did sort of implicitly, and I've heard it stated explicitly in presentations after the paper, that packet loss is a primary control signal. This wasn't stated as an explicit principle, but it was stated that packet loss as a sort of a last resort signal is sort of makes the most sense because it tells you when you've done something wrong. Packet conservation, one of the very fundamental ideas from that paper is about the idea that you keep at most a constant amount of data in the network. And the acts and the data clock each other. The mental image that I often use is a pair of jugglers passing bottles back and forth, putting messages in the bottles. And there's a constant window size, which is the number of bottles circulating. It controls and clocks the whole system, in fact. Congestion control. Sorry, I'm one of the problems with working from home is everybody's working from home.
What I think we'll do, Matt, is I'm going to mute your video. That may help us a little bit.
Just adjust the number of bottles. Okay. We're having video breakup. Okay. Control just adjust. Okay. Congestion control adjusts the number of adjusts the window size, adjusts the number of messages in flight, and as pointed out in Van's paper, these algorithms together have a very, very good measure of intrinsic stability. An important derivative of packet conservation is self-clock. And the key idea here is, let's see, is my cursor visible?
Yes.
Okay. The key idea here is there's a standing queue at the bottleneck queue that then drive the clocking in the entire system, because the acts coming back to the server tell the server when to send data, they tell the server when to wake up the application, and they sort of schedule the whole thing. Self-clocking was a natural way of making TCP scale invariant and completely adapt over what has been 40 years, well, since Van, I guess it was 30 years of evolution since self-clocking became a standard. So sort of taking a step back, 40 years, there have been more than 150 RFCs and hundreds, I said hundreds, there's probably thousands of papers and open source code on making improvements. A very small number of those documents actually change packet formats and core state machines, things like window scaling, selective acknowledgement. The vast majority of them are evolutions in the heuristics and in estimators and such that make improvements on how efficient and TCP uses the network. So one of the properties, one of sort of those, I'll put it this way, a fundamental property of a heuristic, because there's not a fundamental right way to do it. They're all estimators. They all are trying to guess at what's going on in the network. And heuristics that are good, that were good at a particular date in the network, become stale. They stop working. The example here, I'm talking about whether or not RTO is too fast or too slow. If it's too slow, you elapsed time for the user, for the application. If it's too fast, you waste bandwidth. All of the heuristics and all the measurement tools and all the protocols have this property. They don't affect the overall correctness of the protocol, but they do affect how efficiently the protocol uses the network and how effective it solves the problem at hand. I listed here a bunch of categories that estimators fall into. Most of these are not so important for the conversation here. I'm going to talk a little bit about congestion control. But one of the things that's important to be aware of is there's been a huge amount of evolution in loss detection and recovery. And there are still improvements going on. The way I look at this problem is you look at the network and you count things like timeouts, which generally meant you missed an opportunity to recover data. You look at things like DSAC, which means the receiver got duplicate data. You look at a bunch of things like that, and you keep on finding corner cases that the network throws at you and improve the algorithms. Up until maybe the mid-2000s, TCP actually did very poorly if there was both reordering and losses. And a lot of that code has gradually been fixed. Things like early fast retransmit and such have fixed it. These other things are CPU and performance optimization. The auto-tuning, the optimal buffer sizes is very, very important to get you to square one. But once that was in, there's been some tweaks to it, but it's not changed so much. Congestion control is hard. I just looked at the Linux upstream. There are 14 different algorithms in the code. In vast numbers, I do not have a way of counting the number of papers there have been proposing new congestion control algorithms. They're endlessly going on. My microscopic model sort of pointed out implicitly that there's a scaling problem in congestion control. And in fact, in general, in loss-based congestion control, there's a pretty fundamental scaling problem. There are ways of working around it with loss-based, but other signals such as delay sensing, ECN, but there's a bunch of them, might actually scale better, but they turn out to be fragile in deployment. They don't work in certain environments, and if they don't misbehave in certain environments, they're not appropriate to deploy in unattended situations. You can deploy them on a server, which is curated by somebody who pays attention to it, but they're really not safe to ship in consumer-grade machines. One exception possibly is compound, which automatically switches between a couple of different modes depending on whether or not it thinks its delay sensing mode is working correctly. So, a complication on the self-clock. Although self-clock sounds very nice, there's a whole bunch of ways that the network and the end systems reduce the number of acts. Delayed act is a fairly early part of the specification. But in fact, there are lots and lots of things, delay acts, that thin acts, that suppress acts, that merge acts. Even Wi-Fi messes with act timing. It thins acts. Most wireless networks do. In parts of this world, we see networks that give you 1 act per round trip. We mean Google. 1 act per round trip. No self-clock there. The sender sends full-size bursts. So reducing the acts doesn't change the basic nature of the self-clock, but it means that the sender's got to send little bursts for every act that acts more than 1 packet. And this is kind of fundamental to self-clock. So why BBR? This was a talk, an adaptation of a talk that I gave at a Stanford buffer sizing workshop from some work that Andrew and I did actually previously at Google. It's, well, some background on the buffer sizing workshop. It turns out that the $64,000 question, or maybe it's the $64 million question, is how much memory do you put in routers and switches? This has been a recurrent question for years and years, and there have been sort of semi-periodic workshops at Stanford to talk about this problem. And they get together the experts in the field, the academic leaders, and actually key representatives from the manufacturers. And they talk about and explore ways of understanding buffer memory requirements. Look at measurements, they look at models, they look at theory, and there's been a lot of good stuff that has come out of this workshop over the years. And I gave this presentation at the buffer sizing workshop. So I skipped to the end. The punchline, the point of the story is we can no longer afford properly sized buffers. They're too expensive. And they are perpetually going to be doomed by Moore's law. Even whether or not you buy into Moore's law is dead, even if Moore's law was not dead, you can't afford the buffers. Small buffers doom self-clock, and we need to change the end systems. We need to break self-clock, and we need to go to pacing at scale. And BBR is a start. And so my question was to them, to the community, is not how do you measure the size of the buffers or the buffers needed. It's given a buffer size, how do you construct the end systems to fit within those buffers? So Moore's law. So the commonly uttered version of Moore's law was not actually uttered by Moore himself. But the common expression is the speed complexity product doubles every 18 months. And this has been borne out over a long time, over a lot of technologies. Recently, when people say Moore's law is dead, what they really mean is the chip manufacturers are spending all of their increased complexity, all their increased fab on complexity rather than speed. The speed is maxed out and complexity has been growing. Most of the growth has been in complexity. However, if you look at the internet and the kinds of speeds we see for link rates, the doubling time over, again, I look back over 3 decades, is really close to doubling every 2 years. That is the generations are roughly an order of magnitude, and they're a little bit more than 3 years apart. And so you get the staircase, which is 10 megabits, 100 megabits, gigabit, 10 gigabits, and so on. And that staircase has got a slope of doubling every 2 years. In order for the drain time to be constant, which is the amount of time it takes for a full buffer to empty, the buffers, well, first of all, fundamentally, the buffer speed has to double to match the link rate, and the buffer size has to double to maintain the drain time. So the speed complexity product has to quadruple every 2 years, or double every year, which is faster than Moore's law. And it can't be done. It simply cannot be done. And the consequence of this is that buffer drain times keep falling. And I'm going to tell an anecdote that actually came up at the microphone when I was giving this talk. If you look at certain high-end carrier-grade switches and you pull a switch card out of it, you look at one side of the card and there's this big flat black chip. That's the switch itself. And it's big and flat because it's got a large number of pins on it. It's a rather unremarkable chip other than it's got a lot of pins on it. You flip it over and the card is completely covered with memory chips and heat sinks because the memory on that router card runs perhaps 2 orders of magnitude hotter than the switch chip. It's the memory that's the expensive part. It's the memory that's using the power. It's the memory that needs the cooling. The switching part is easy. So we've got those problems. We can't run big, as larger buffers as we would like to have. And this is why the buffer sizing workshop is such an important question. So returning back to protocols, there's a whole lot of reasons why you want large buffers. But the real problem is packet conservation and self-clock. When you have transmissions triggered by ACKs, the entire system depends on this queue at the bottleneck. And that queue in the bottleneck represents the amount of time which the clock can run sort of when there are interruptions, when there are gaps, when there are disturbances in the traffic. And this is real easy to do if the queue is large, but if the queue is 1% of the amount of data in flight in the network, it's sort of fundamentally unstable. You can't keep it on the rails. And this problem, this limited memory size, is sort of the thing that's been driving the congestion control. Actually, once I realized this, it became apparent that avoiding the consequences of the short buffers has been a big design constraint on protocols and congestion control. That the real point of congestion control is to try to overfill buffers that are too small. So BBR takes a completely new approach. And I'm running really fast here. Oh, that's okay. The way that BBR works is it builds an explicit model of the network, and I'll get to how it does that in a moment, but you assume that you have a model which you know the maximum bandwidth. You also need to know the min RTT for sort of the side issue, but the important things, you know the max bandwidth, and you just send data on a timer at the maximum known bandwidth. It's not self-clocked. It doesn't do packet conservation by default. It abandons these two core Van Jacobson principles. I should say that this was actually largely designed by Van Jacobson. So Van Jacobson is undoing his work from 30 years ago. And the way you get the models is you did the pacing rate to observe whether or not you actually understand what the network is doing. You observe when you do the pacing rate, you can say, when I go up a little bit, either the data delivery rate doesn't go down or the delay goes up. I could do it either way. If I go down a little bit, if the RTT doesn't go down, I'm actually at min RTT. If when I slow down a little bit, the RTT goes down, then I'm not quite at the min. And it uses these experiments to measure the network. So the personality of BBR, how it plays with others, how it shares with Cubic, how it shares with itself, are all determined by the heuristics that it used to dither the protocol. And the heuristics that it used to dither the protocol sort of aren't mainline code. They tweak things as it's flying along, but they aren't sort of fundamentally imposed states in the code. And the cool thing about it is you can add additional algorithms to do different kinds of measurements. And these algorithms also easily play well together inside of BBR. It turns out that the natural operator to use to combine, for instance, estimates the data rate is a min. I get a whole bunch of different min estimators, and any one of them that says, you shouldn't go any faster than this is probably the one you want to honor. And this insight has actually changed my thinking about a whole lot of issues about protocol design and congestion control. But I haven't had a chance to explore that so much yet. So let's look at some cases. This is not an ESNet environment. This is a Google/Facebook/Netflix/ environment. I imagine a server with a 10 gigabit interface serving across the internet to a client which has got, let's say, a 1 megabit bottleneck, really fairly slow bottleneck, the details here aren't important. I imagine this is being multiple high bandwidth connections together, and the switches feeds data in. But the important part is the server here estimates the bottleneck here and paces data through the whole network such that packets arrive at the queue at the far end just as they're leaving the queue. So the server maintains a steady state small queue near the client, even though in spite of or independent of anything that's going on the forward path. The traffic actually ends up being smoother than random arrivals in a statistical model. And it's very easy to construct environments where you run with no significant queuing in the core. And it's very, very hard. You can imagine situations where the pacing clocks in a server somehow become synchronized and you get bursts of packets. But normally the packets are all interleaved. I see a question. So they have done some experiments with ECN. The ECN community is doing some major, I'll say, arm wrestling about how ECN should work and how the new ECN should work. Something to replace traditional Sally Floyd style ECN. And they have, I actually don't remember the details of the algorithm, but the framework algorithm in BBR v2, the framework algorithm demonstrates basic ECN functionality in a style that is similar to one of the proposals for the next generation ECN. And the people who are implementing it have stated that they will be compatible with whatever the ECN community agrees on. There are some hard open questions there, significantly having to do with treatment of short queues and such. Anyhow, the nice thing about this case is, as I said, the data coming out of the server is smooth to match the bottleneck at the client, and is very low stress on the rest of the path. If you compare that to the self-clock situation, where I have a bottleneck at the client, again, and the client is setting ACKs and somebody is thinning the ACKs, the server ends up sending these back-to-back packets at 10 gigabits per second, sort of needlessly. They propagate as a train across the whole network. And it only takes 11 concurrent bursts from 11 servers to actually start causing a queue here. This traffic is very noisy. It's much noisier than random arrivals. And that's why they need the queues. And it's very, very expensive. And just the difference between these two environments is a huge economic driver for the large content providers. This is why Google is working on BBR in the first place, and also why Netflix is investing in BBR for BSDs. It fundamentally affects the amount of traffic these near switches can carry, and saves you on expensive memory. So, but there's a flip side of this. Deprecating Van Jacobson 88 is a sea change for all of the research. All of the research that we've done in congestion control has these assumptions baked into it. And we don't really know what we think we know that is wrong. That's the way I put it. The things I think I know that are wrong. And getting my head around how the world might be different in a BBR world is really hard. I have this hunch that there are some really cool ideas that were discarded because it didn't work. And there's lots and lots of things which need to be revisited. The reason I say revisited is because some of the answers are the same. Some of the answers are different. And you actually need to re-ask all the questions we've been asking in the last 30 years. I mentioned a little bit about how the BBR framework is is easily adapted to take additional algorithms. I see there actually being a boom of people actually putting in a lot of these algorithms. One of the things I would love to see is chirping. Chirping algorithms are, for instance, much more compatible with a paste TCP, and there are certain environments where chirping works. Chirping is a method of measurement where you send packets in typically a geometric sequence of timing, and you measure how the network changes the timing. So, lots of work to do. Jamshid Madavi and I wrote an editorial for, this is the 50th anniversary edition of CCR, where we reflected on past work. My microscopic model paper got a Test of Time award, for which I thank them by saying it needs to be deprecated, and that was 10 years ago. I'm now saying again, it really needs to be deprecated, because the model accurately reflects reality in Reno and cubic class congestion control, but that reality is not good for the network. Is not what we want. So there's also, and this is more relevant to the buffer sizing talk, I also had a list of open questions, things that are sort of consequences of the way self-clock works, that I was trying to solicit researchers to take up. I can't do more than a tiny bit of these. Somebody else needs to work on them. And finally, echoing the spoiler at the front, Moore's law completely dooms large buffers. Small buffers doom self-clock protocols. Pacing is inevitable. I believe that BBR is a good start, and everything is going to be different. And I will take questions.
All right, well, thank you, Matt. So people, please type in your questions into the chat room and I'll read them off. You've already answered Eli's questions. So the next one that came in was from Alan. Does Multistream BBR work well with Linux FQ max rate?
Gee. So here I get into trouble. I'm not actually, I was involved a little bit in some of the BBR v1 work, and I've had to step away from BBR v2. BBR v2 works much better. They put in explicit algorithms to handle some of these cases. And in particular, one of the things that they did in BBR v2 is they put in a mode which mimics, I'll put it this way for this community, it mimics some of the lameness in cubic. You might have opinions as to whether or not that's a good thing, but the point of mimicking cubic's lameness is it matches, it's fair with cubic over a fairly wide range. Actually, cubic and Reno over a fairly wide range of space of network parameters. I actually haven't been able to get an answer to the question that I care about, which is at really large scales, does it fail to fill the network the way cubic does? I'm pretty sure that they didn't do that, but the sharing has gotten a lot better in all regards. It was a huge amount of the part of the attention in BBR v2, because the complaints BBR v1 does not use loss as a signal at all. And there are some cases where the network doesn't give you any clue that you're overwhelming it, and BBR and TCP is now capable of repairing 5 or 10% losses without any problem. And if the network kept delivering more packets and you were running at 5 or 10% loss, BBR would say, things are peachy, I'll just keep plowing along. Well, at that kind of loss rates, nothing else gets done, including DNS and stuff like that. I mean, it was obviously not a good situation. Nearly all of that has been fixed. So is there a way, I don't see how to see the chat room.
Well, I'll read off the next one here. The follow-up by Alan was, how can we start using BBR2 today?
So I haven't looked at it recently. BBR v1 is in the 5.4 LTS. The BBR v2 required some instrumentation changes in the main line, and so the default way of doing it is if you can build a kernel from next, and the BBR v2 patches are posted in there against a next kernel. I actually, it's been a while since I've looked exactly where they are relative to the head of next.
Okay.
So.
And
Yes.
Andrew.
Somebody posted the URL.
Yep.
Yeah.
And Andrew shared the URL. So the next question was from Eli. It seems that because CPU clock rate growth is essentially flat, we need parallel applications in order to achieve high per task data transfer throughput. How do we harmonize this with BBR?
So, so here's a place where the ESNet community can contribute, because part of the problem is the industrial users of BBR are faced with two cases. One is we're serving users, and users all have paths like the ones I described. There's a bottleneck near the far end, and typically only one or two streams, low aggregation at the actual bottleneck, and it's very well studied. And the other case is very, very, very heavily sharded flows, which are RPCs, which are mostly application limited. And so Google internal search services and such like that runs in this kind of environment. And there are some cases which are being studied inside of Google, but we don't have any workloads. None of us have any workloads that are, I'll say, small integer parallel flows that actually fill the link. 10 flows that fill the link, and or even 100 flows that fill the link. They're all either thousands of flows, or they're RPCs or something like that. So there's some experiments in that space that would be really good for ESNet in particular, and the research and engineering community in general to participate in and actually find out some of the pathologies. It is true from a protocols perspective, it's a fundamentally harder problem. And the reason it's a harder problem, if I have one bottleneck and one flow, I implicitly have to only model the bottleneck. It's fundamentally naturally a two parameter model. If I have inflows, I actually have n+1 state variables, being the link, the queue occupancy and the link bandwidths for each, and the utilization for each of the other flows, link rates, data rates for each of the other flows. And the controller in BBR has to do something intelligent now where it's contributing a minority of the complete load. And there's all sorts of ensemble synchronization problems and things like that, which Google isn't interested in and doesn't have a test bed for. And you guys care much, much more about that. It is my belief it is capable of being made to work well in that state. And one of my clues is that I would like to explore improving the modularity of the framework, if you wish, and people can just plug in algorithms easily. Sub-congestion control modules. The next question.
Sure. The next question was from Ellie. It was shown that BBR does not coexist well with loss-based congestion control like Cubic. Will BBR replace entirely Cubic, or will they coexist in the future?
So the BBR1 was not polite by any measure, and the case that BBR1 crushed Cubic was on short queue, heavily aggregated paths. BBR v2 has got this compatibility mode, and I remain open-minded and unbiased by data as to whether or not the Cubic compatibility mode is going to haunt us. I have this fear it will haunt us, because it means that some of Cubic's lamenesses have been ported into BBR, in order to solve exactly this problem. Excuse me. Next.
Okay. The next question was from John. They recently enabled BBR on a cluster of machines. It dramatically improved poor performing paths. Is it safe to upgrade to BBR2 on a very active cluster?
Again, I'm a little bit lost in the details. There is unfortunately a regression, and it has to do. I don't remember the case. You actually need to do the experiment. Problem that there's some cases where BBR v1 was too aggressive, and making BBR v2 less aggressive means that there's a few cases where BBR v1 outperforms v2. However, they are somewhat anomalous cases in the sense that they represent environments where it's probably not healthy. For instance, excessive loss rate. I mean, BBR v1 will very happily run at much too high a loss rate. And so the argument that you really want to go to v2 becomes a little bit more complicated. And this is actually some of the conversations that are going on now in other places.
Okay.
By the way, the generalization of that problem haunts me. I have this fear that BBR v2 is too aggressive. 3 is going to have deployment problems without even knowing what might be in BBR v3. So,
okay.
So I can actually read the questions. What's the difference between BBR in Quick and TCP? I would have to look at the code. They're in very close agreement as of a particular date. There are a few details that the Quick people, things that the Quick people have to do with differently. They have less precision in the timers, for instance, and stuff like that. And the other issue is one of the fundamental reasons that people were going with Quick is since it's not in the kernel, it's actually more agile for experimentation. And it's still more agile for experimentation. And so there've occasionally been new and Quick ahead of in BBR. Okay. How frequent are the max bandwidth min RTT predictions updated? Okay, so this is one of the things that has changed very much between V1 and V2. In BBR V2, in both of them, the min RTT estimator runs every 10 seconds, and that 10 seconds is trimmed such that the goal is that everybody in the universe is likely to do it at the same time. There's some relativity things you could say about the infeasibility of that, but at least locally, everybody does it at the same time. And which means that everybody takes a slight pause and all the pauses overlap, and the small amount of data that you send pause, you get a really good measure of the minimum round trip time. The thing that they changed in BBR v2 is they made the bandwidth estimation resemble the macroscopic model formula. That is, they made the bandwidth estimation proportional to the window size, the frequency of the bandwidth, the interval of the bandwidth estimation proportional to the window size. So as the network goes faster, you estimate the bandwidth less frequently, which means it gets sluggish in the same way that Cubic gets sluggish. But it induces losses in the network with the same pattern as Cubic does. And that's how they got the Cubic compatibility. BBR v1, the bandwidth estimation was every 8 round trips, which is part of why it crushed Cubic. So, and I think that's all. I have no other questions. Yes, I've been a little distracted this week. Didn't have as much material as I wanted to, but Anybody
All right.
else?
All right. Well, we'll give it a pause in case anybody has any last questions. Thank you again, Matt, for taking your time out to do this. I think it's been great. A lot of people within the community are always asking about this, and you're charged to us to perhaps get some of our high-powered machines installed and testing this. I think many people may be interested in doing that.
Yeah.
So we'll certainly reach out to you if we have additional questions or feedback. Or
I just thought of something I didn't add. It does run as a loadable module, and so if you go to an appropriate base kernel, you can load BBR v2, run some experiments, unload it, load it, recompile just the module, load the module, and then you can flip it on for one flow. So you can do experiments in machines that have, I wouldn't do them on big production time sharing machines, but you can do them on machines that have other users, that have other activity, which is a big help for experimentation. So, or you can do them on dedicated machines. So,
okay.
last slide.
All right, and Tim noted perf sonar could measure bar and something else, or BBR and something else over time. So yeah, I think that's kind of what you were saying.
Actually, we have a version of NDT in the wings that'll be BBR based.
Oh, perfect.
We are currently testing it, and it's actually running on the new fleet, but the service is hidden. The new MLab fleet is running BBR, thing that we're calling MLab version 7, which got BBR underneath it. Okay.
Well, one more. Your old colleague Michael wants to know: does BBR exist for any of the BSDs, or is it just Linux at this point?
So the Netflix folks are doing it for BSD, and Randall Stewart, who some of you may know from SCTP days, is the chief technical person on that project, and they're quite excited about it. Last time I talked to them, it's been a while. I don't know how far along they are. The hard part is the hard piece to build is actually the pacing machinery. The BBR depends on a packet scheduler that builds a calendar queue inside of Linux that can do 1 million concurrent flows lockless. And that technology is sort of fundamental to making it go. It's in the upstream, or there's a version of it in the upstream at least. So, okay.
Okay. All right. Thank you so much, Matt. And everybody, we'll get this posted up to YouTube. And we will have a talk next week as well, but I don't have the list in front of me. So just look out for the announcement on the mailing list. Everybody have a good weekend. We'll talk to you soon.
Thank you.